I don't know. I kind of think that it's not an issue of they're out of touch. I think it's becoming an issue of they've invested into the system and they want to make it work. They don't want to look bad. It's going to be my impression. It's just absolutely ridiculous. Yes, when I get that write up, I'll show you.
All due in one day.
That was all due in one day, along with all the other classes. I mean, my daughter's math assignment was a worksheet, and then she had to do a unit test. But the problem with that was you submitted the worksheet that was supposed to be graded, and once it gets graded, then the exam or the unit test gets unlocked. So who's going to actually grade all of these papers that are coming in, and who's going to grade them right when they get in so that the unit test could be unlocked? I don't know. From our understanding, these teachers are covering multiple classes and probably have several hundred students in these classes. So they don't get to it. They don't get it graded, which means the students don't get to take the test, which means they are now marked as being behind. And somebody else actually counted up the units. So it's supposed to be 18 weeks, I think. 18 weeks in the class itself, but in the semester, there's only 17 weeks in the semester. So there's no way to actually get to 100% completion rate unless you start doubling up, which they didn't do. Oh, gotta love it, gotta love it. Gotta love it. All right, let's see, let's finish getting my attendance just in case one of you tests positive and they say we need to know who they've been exposed to. So, Francisco came in. Yeah, you can't do it. You can't watch 2 movies in 15
You can't watch one movie in 15
No. And then I started struggling because I'm thinking, man, what movies would I have watched? That's what I got hung up on. What movies?
Oh, I was quick.
So I think they did Fame, maybe the original and then the remake. I forgot. I've never seen the remake.
Like
Which one?
Godzilla used to be fun.
Godzilla.
There's so many different Spider-Man.
So yeah, my initial thought was like Ocean's 11, believe it or not,
Okay.
the original and then the remake, and I thought, oh, that would kind of be a good one. And then my wife brought up Ghostbusters, and it's like, yeah, that new one just kind of went out the door because I didn't care for it. And I honestly don't remember the new one that much. But yeah, the Spider-Mans, or I guess Hulk,
Yeah.
the Edward Norton one,
Oh man.
Yeah.
and then the remake.
Well, see, there hasn't been a Mark Ruffalo standalone Hulk. So I think the Edward.
No, there's an older
Would you
Hulk.
any
There's
version
an
of
older
Spider-Man?
Hulk.
Yeah. There's one pre-Edward Norton where the CGI is pretty embarrassing.
It's rough.
I think.
Okay, we're not CGI.
Yeah.
I guess did Fantastic Four also do a remake?
It did.
So I remember the original that came out, and yeah, it was.
I didn't watch the new one.
I like my
I heard you guys did.
I haven't.
What did they end up watching?
I think Fame.
Oh, when they remade
I thought you said The Thing.
No. Oh
That
no.
was like, that's a pretty dark thing.
It's not great.
No, Fame. So I guess the Dan. I remember the older movie that came out. So I don't remember the new one. But then I started thinking, oh yeah, what about like the Stephen King's ones? So you got the movie and then the miniseries,
Oh yeah.
and those are 2 different times. And yeah, as we thought, said, wow, that's definitely going to be longer than 2 hours. So, what did y'all get into? All of the YouTube crowd is missing our excitement of the fantastic.
It takes a while. Maybe I'm just slow. I think they made a lot of the thing. I guess it like regenerates a new each time.
Live stream?
Yeah.
Yeah, so yeah, for the live streams, I rename them.
Oh, okay.
So
Okay.
I can't, if I start a new live stream and give it a new name, it'll generate a new link. So just to maintain the same link, what I'll do is just edit the titles, and then after classes, what I'll do is I'll change the titles, change the descriptions to match what we actually covered in the class, and then I move it or I assign it a playlist into our our biostatic
It
limits.
popped up, it took me a minute to see that.
Yeah. So that's where we'll get it. All right, so we kind of very quickly left off with the mode. We ran out of time. So just quickly, the mode is the common value in our frequency distribution. You can say it is a measure of central tendency. It's the peak in the histogram, and what we typically look for if we're looking at the mode is how many peaks do we have. So a normal distribution should only have one peak. If you do a histogram and you get 2 peaks, you've got probably some problem, all right? And that could be a category, a grouping problem. So maybe you have two groups in your data set, even though you suspected that it was only one data set. The use in biology is limited, although we do see like most common traits, most common phenotypes being reported. So if the mode gets reported, it's usually tied to systematics or morphometrics, type analysis. That's our mode. That's 2. There it is. All right, so central tendency review. We have the mean. That's usually preferred. That's the one that we're going to typically report. All right. The means have the smaller standard errors associated with it, and we haven't talked about standard errors yet because that's part of our dispersion, measures of dispersion. But this is one reason why mean is preferred. All right, it's easier to work with mathematically compared to all the other ones. And it's got some very interesting properties in that the mean of means of samples, so sample means, tend to be normally distributed even if the underlying data are not. So if you have a sample and the actual distribution of the sample is, let's say, a chi-square distribution, if we take repeated samples of that chi-square distribution and calculated a mean each time, then the mean of those means, so the collection of means, would approximate a normal distribution. And that allows us then to make comparisons among the means. So it's a pretty cool property to work with. The negative, though, of the mean is that it's affected by outliers and it's affected by the shape of our distribution. So we said when we talked about balance points that if we had a very skewed distribution, this heavy tail in our distribution is going to pull the mean towards that tail, all right? So it's going to tend to pull the mean towards that tail because our distribution has this heavy tails. And we'll talk about these distributions when we talk about assessing normality, all right? Also with outliers, so if we have points where most of our points are like this, but then we have a point that's way out there, our average should be something closer to the middle, but our average is going to get pulled up because of that one outlier. So means are sensitive to outliers and shape of the frequency distribution. Can we get around it? Yeah. I mean, just by definition, if we're not normally distributed, we're going to have a different shape of the distribution. But in most cases, because we're working with samples and repeated samples, the collection of sample means approximates that normal distribution, so we get around it. Median is going to be the second choice. So if we're non-normal, then usually we try to utilize the median. It's not going to be affected by outliers or shape of the frequency distribution because we're only looking at 50% points. So we're looking at quantiles, percentiles, and so forth. All right? Means usually preferred. Median would be the second choice. If we do have a normal distribution, then what we're going to see is that the mean is equal to the median, it's equal to the mode. So all of those are going to be equal if we have a normal distribution. If we're going to be skewed, then our values are going to be different. So here is an example of a skew right distribution. So it's skewed right because we have this heavy tail on the right-hand side of our distribution. I tend to remember it as saying skew right or we're leaning left. So our normal distribution just should be like a bell curve like that. all right? But what ends up happening is that our data gets skewed, so the curve starts to lean one way. So we lean left, which means we're skewed right. We've got these values. So if we have a right-hand tail, like this, then our mean's going to be larger than the median. So our median's going to be someplace around there. And then our mode represents that peak. All right? If they're normal, then all three are at the same point. It's the opposite if we are skewed left. So if we have a distribution that looks something like this, now our average is going to be someplace right there. Our median is going to be someplace right there, and then our mode represents that peak. So those are our relationships when we're not working with a normal distribution. All right, any questions on central tendency? All right, sample statistics and populations. All right, we've been introducing sample statistics, the mean and the medians. All right, these are sample statistics. We use these to estimate our population parameters. So a population is going to have a mean. It's going to have a median. All right. We also have statistics and parameters for our dispersion measures. So our variance, S squared, that's a sample variance. That's going to approximate our population level variance, which is sigma squared. Now, when we choose these measures, when we choose these statistics, we always strive to have unbiased estimators. Estimators that are unbiased means that our sample statistics equal our population parameters. If they're not, then what we typically see is our sample statistics tend to be smaller than the actual population parameter. We say that they are then biased. All right? So, of the sample statistics that we encounter in this class, sample mean and variance are considered unbiased estimators. So when we calculate them for the sample, our population parameters should be the same. Sample standard deviation, however, is biased. All right, it's going to be lower than the true population standard deviation. Does this matter a whole lot? Well, if we have a really small sample size, yeah, it might matter. But the reality is that we typically have a sample size large enough where we can ignore that bias. Why can we ignore it? It's because the difference is going to be negligible. It's such a small amount, we're biased by such a small amount that we can just ignore it. Why do we say this? It's because we're always striving for these unbiased estimators, but we have to recognize that not all of our sample statistics are unbiased. So let's move to our dispersion measures, because our medians, our central tendency measures are unbiased. It's our dispersion measures that tend to be unbiased, or can be unbiased. All right, so first up is the range. You've encountered this range. I know you've encountered it in elementary school, probably repeatedly. All right, the range is simply smallest and largest value of our data set. That's all it is. All right? Now, how you report the range could be different. It could be the smallest and the largest value in our data set. That's what you can report. Or you can actually do the difference between the largest and the smallest value. All right? And this is why I put up in the slide. I'll accept the largest and smallest values or the difference of these values because either one is appropriate. It's just stats programs will give it different ways. Our summary function in R will give the minimum and maximum value in our data set. That can be used as our range. All right? Or we can use the diff of our range, which is the difference of our range of values, which can also be used as a range. I present this because I think in a textbook, you'll see range as being the difference between the largest and smallest values. All right? That difference doesn't mean a whole lot because normally when we ask about a range, we want to know what's the smallest and the largest value. All right? So if you do it by hand, it's very easy. Just find the smallest and the largest value. But how do we do it in R? R, we're going to use the range function. All right? So the range is going to give us our smallest and largest value. So let me open up RStudio, get this going. this over here. All right, so we did measures of central tendency. Now let us introduce dispersion. Measures of dispersion. So first up is our range. Move these down. All right, so the function is range of x, where x is our numeric vector. All right, so that's going to be our function. All right, so when I open up RStudio, I don't have anything in my global environment, so I will go ahead and run. There it is. Generating the data set for my lecture, I'll run that chunk, and I get my AV1, AV2, AV3 again. All right, so range of x is where x is our numeric vector. So just as an example, I'm going to create just a sample data set DAT just to demonstrate this, and I am just going to do just a set of numbers, just so we can demonstrate it. Something that we can see, it's small. I can look at it and tell you that my range is going to be 2 to 10. Okay, I can see that, and hopefully you can see it too. So then when we just run range of DAT, all right, we should get the values 2 and 10. So I run the chunk, and that's exactly what it gives me, 2 and 10. All right, so just kind of as a review, our exam's coming up next week. You know, I might ask you, hey, what is this function? Well, I created a vector, right? I created a vector, that's my C, my combined, right, of these numbers, and I saved it as the object DAT. And then I calculated the range of DAT. All right. The other way, if you actually wanted the difference, minimum and maximum values. All right, so we're going to use a different, so what if we wanted the actual numeric range? You know, so from 2 to 10, how many units is that? All right, then what we could do is use the diff function, diff for difference, all right? But with the difference, we have to provide it 2 values, because it's going to find the difference between 2 values. That's where I say where x is 2 numbers. Now it's nice because what we can do is pass our actual range, because range gave us 2 values, did it not? It gave us 2 and 10. So what we can do is pass that range right to our diff function to get 8. So diff of the range of DAT, and when I run that, I get 8. All right, how useful is that? I don't know. It just kind of depends on who your major advisor is. Maybe they want it, maybe they don't. All right. Questions? So range is pretty easy. Range gives us a general description of dispersion. All right. Key thing with this, and I say it's general, because our range is going to increase as our sample size increases. If you can think about it as we've got a histogram of numbers, all right? Raise this down. And we're going to come back to skew. You'll spend a lot of time on this. So imagine that we have a population, and our population can take any number from this distribution. If we take a random sample of 5 numbers, I think most of those 5 numbers, or at least with a high probability, they're all going to come from this central peak. As we keep adding samples,
as we keep drawing a random number, we're going to make it more and more likely that we start getting into our tail region. All right, so as our sample size increases, our ranges are going to also increase, and that doesn't really reflect the true dispersion of our data set, because what we're really looking for is this peak. How wide is this peak? And the range doesn't really capture that. Also, our range is going to be sensitive to outliers. We have outliers in the data set, they're going to factor into our min and max value. So before we go on, is there another way to do our range? There is. So there's a summary function here. All right, there's a summary function, and it's just summary of x, of whatever our object is. All right, now notice I just said where x is a vector, I could take that out and just say where x is an object. Because summary is going to work on a lot of different objects. It's going to work on a numeric vector, it's going to work on a character vector, it's going to work on a data set. All right, it's going to work on a lot of different things. So what we can do is pass it our data vector, so summary dat, and see what it gives us. And what you'll see is it gives us more than just the range. It gives us our minimum value, that's our min. It gives us our max value, that's our 10. All right, it gives us the first quartile, the median, the mean, and the third quartile. It gives us a lot of information, right? So a lot of times I just do summary to see what it looks like. And just like a histogram, if I have an outlier, it's going to stick out. So if I forgot, a decimal point, maybe this is going to be 10,000 instead of 10, and I'll see it and say, ooh, yeah, that's not right. But it's just another way to calculate ranges. All right, so that's a range. Interquartile range. Interquartile range is the difference between the first and the third quartile. All right, this is going to be a very good measure of dispersion that represents the main part of our distribution. All right, maybe not numerically, but percentage-wise, because it's going to give us the middle 50%. All right, it's going to give us the middle 50%. It's also unaffected by outliers because we're looking at the middle 50%. In general, if we're going to work with medians, then our measure of dispersion that we report will be this interquartile range. How do we do it? Well, one, we can look at the summary. So our summary, the interquartile range, is from 5 to 8.5. All right, that's reported. Or we can use R's built-in function, which is IQR for interquartile ranges. All right, so IQR, all capitals, will calculate the interquartile range of a numeric vector x. That's what it does. All right, and it also has the option of removing missing data, so na.rm equals t, if we have missing data. So if you don't know if you have missing data and you do IQR of the vector, it'll return NA if you have any missing data. All right, so let's do that with our data set. So we did range. Next up is interquartile range. IQR of x, where x is a numeric vector. All right, so it's just IQR. We don't have missing data, so I'm just going to do IQR of dat. And when I run that, I get 3.5. Just like the range, you can report interquartile range as the first quartile and the third quartile. Right? The summary function gave it to us, so we can report it as 5 and 8.5. Or so 5 dash 8.5. So from 5 to 8.5. That's our interquartile range, or you can report it as 3.5. So that way we know it's 3.5 units centered around the median. So 1.25 below the median, 1.25 above the median. We could also use a quantile function to get our quartiles, right? Right? Any other questions? Okay, so range and interquartile ranges, pretty easy. I think they're pretty easy to understand. The next ones are going to be a little bit harder, because now what we're looking for are measures of dispersion when working with the mean. All right, so the range could be, you can report the range for any type of data set, any type of numeric data set. If we're going to report the mean, we report the interquartile range. But what if we're reporting did I say that wrong? If we report the median, we work with the interquartile range. If we report the mean, we're going to report something different. All right? So it all starts with deviance. All right? A deviate is a difference between our observed value and the mean of our sample. All right? We're going to see a deviate a lot throughout this class. All right? So the way we can look at it in terms of deviance is to say we have data points. All right? We've got different values, and this will be like item number or whatever, sample number, and that line represents our sample average. All right? We have item number 1 is there. Item number 2 is there. Item number 3 is there. Item number 4, maybe right like that. So we got item number 1, 2, 3. So a 4 sample data set. All right. Taken together, when we calculate all of the x's, we get this line. All right. A deviate represents the difference between it from each point to that mean, to that sample mean. All right. Now, deviate started out as being the first way in which we could describe dispersion, but it came at a really at a pretty big problem. And that problem was that as we add samples, it kept increasing in size. All right, it kept increasing in size. I'm sorry, I take that back. As we kept adding samples, it doesn't change because the sum of our deviates, because whatever our deviates is going in one direction, we have equal amount of deviates going in the opposite direction. The magnitudes can differ, but the sum of our negatives will always equal the sum of our positives. So when you calculate like this, you'd say, okay, I've got these deviates, let's just add them all up to get an overall view of dispersion. It all added to 0. So then people said, well, we can get around that by squaring each of our deviates. So take that and square it. All right, now what's happened is it's taken the negative values and made them all positive. So now as we calculate our deviates, our sum of our squares of the deviates and add them up, now we're actually getting a better idea of the dispersion, but at a cost because this is going to keep increasing every time we add a data point. So every new data point is going to have its own sum of square deviates. Now I've said this is sum of squares. That's what this term actually is. So we started with the deviate and then we squared it. All right. So the sum of squares will reappear throughout this class. All right. And this was the equation. So this sum, the sum of squares, SS, is equal to the sum of the square of our deviance. That led then to people to say, okay, well, if this number keeps increasing in size, perhaps we could scale it based on the sample size. So take the sum of our square deviates, take all of them together, and divide by the sample size to get an average of the sum of our square deviates. That is our variance. So this right here. So our average was the sum of our vector, right? Divided by the sample size. Same idea. there's our deviates. This is our square term. So we squared each of our deviates. We added them all up, and then we divided it by our total sample size. That gives us a variance, which incidentally is also called the mean square. All right, are we going to encounter mean squares again? Yeah, we will. We're going to see them in the analysis of variance. All right, so the variance represents the average of the squared deviant values. It works to kind of balance out large and small deviance values, so it gives a much better image or much better picture of our overall dispersion. All right, but in this case, this represents our population. So it assumes we have the entire population because we know every single individual in it. All right, that's why we divide it by our total sample size. But normally we don't have that value. We don't know what the actual population parameter is. So what ends up happening is that we estimate it using our sample statistic. And when we estimate it, what ends up happening is that we have to decrease what is called our degrees of freedom. And how we decrease it, in this case, is to subtract 1 from our sample size. So instead of working with a total of, let's say, 20 data points, we lose one of those freedoms because we estimated our sample, or we estimated our population parameter utilizing the sample statistic. All right, so why do we do that? Why do we do that? Well, I told it to you kind of conceptually as to what happens, but here's another way to look at it. If we took our sample and we divide it by our total population size, we get a biased estimator. We're going to be low. When we divide it by n-1, it reduces how much bias we have so that it's effectively 0. All right, so anytime we work with the sample, we're going to work with these equations. All right, this is actually pretty easy to do by hand. All right, it is a lot of work. I'll say it is tedious. There's a lot of room for messing up on your calculator, which is why we'll probably just do it on the computer. Also notice the units. So check out our variances. Our variances are all units squared. How did they get units squared? It's from our deviance. So we had x units minus an average units. All right, and then once we squared it, we're dealing with squared units. So change this. Let's say this is length in centimeters. All right. So our x minus x bar gives us some unit in centimeters, right? Because the units are the same. As soon as we squared it, now we're dealing with centimeters squared. And it stays at centimeters squared for our variances. All right? How easy is it to compare variances if we're dealing with squared centimeters, but our lengths are actually centimeters? Kind of conceptually, it's hard to wrap your head around, right? Length of a wing in centimeters, and then all of a sudden the variance is in square centimeters. It's like, hold on, I measured length, I didn't measure area. So how do we get around that? Well, we take the variance and we take the square root. And that gives us our standard deviation, which is also called our root mean square. All right, so we had a sum of squares, and then we had the mean square, and now we have the root mean square. All of these terms are part of analysis of variance tables. So if you do an ANOVA in Excel and use their data analysis tools, you could probably encounter some of these terms. That's all they are. Sum of squares, the mean square is our variance, the root mean square is a standard deviation. What's great about the standard deviation is that we're back to units, we're back to normal measurement units, which makes it very easily interpretable. All right, so we're not going to do this by hand. I'll show you how to do it by hand for a frequency table. All right, but for this class, we're just going to use R. What are the functions? Variance is var, V-A-R, and we give it a numeric vector, x. All right, just like all of the other descriptive stats, we have na.rm equals t. All right. If we have a vector that doesn't have missing data, then we can leave that off. We can always do the square root of r to get our standard deviation, or we can use SD for standard deviation. All right, so that's why I put here, SQRT is our square root. We can do square root of our var to get the exact same value. So let's go back to our R. Mark down. So we did interquartile range. So now let's do our variance. So this is our mean square of our values, which is basically the mean of our sum of squares. Right, so it's the average of our sum of squares. We can calculate it using var x, na.rm equals t, where x is a numeric vector. So even if it's in a data frame, as long as we reference the variable properly, so data $sign in our vector, we can calculate the variance. So we created that simple vector, dat. So it is very easy just to do var of dat, and when we run it, we get our variance. Now we didn't assign units to those values, we just made up those numbers, but let's say those are, peaches. How many peaches we picked off of a tree? Right, so we had 2 off of one tree and 4 off of another and so forth. So our variance in this case is 7.95 peaches squared. Which, if we ask for the variance of peaches, we'll say, yeah, it's peaches, 7.95 peaches squared, but that doesn't make a whole lot of sense. Right, so what we would probably prefer to use is our standard deviation, which represents our root mean square, or the square root of the variance. All right, our function is SD of x, where na.rm equals t, where x is a numeric vector. So instead of var, we just do SD of our dat. All right, I'm going to run that, and you will see that it is simply the square root of 7.95, which is 2.82. Now, is this the units? If our data set was peaches, this would represent our 2.82 peaches. 2.82 peaches. And just to demonstrate that this is, I will use square root SQR2 of var of dat. So I'm taking the variance of dat vector and then taking the square root of that, and we will get the exact same number. So just to demonstrate that that's all it is. All right? And we can do it longhand too, but why do that? Questions? If we work with a mean, if we report a mean, standard deviation is one of the options that we will use to report a dispersion. Right. It's one of our options. All right, so I had dispersion practice. We already did these.
Yeah, this is an actual graph. That X is like the average, right?
This is our, so our X values would be, say 0 up to 10.
Would it actually come from like the line of best fit, or the
No, so let's just do our data points. So let's say we have, we're working with 2, 4, 5, and 8, all right? So if I'm looking at my data points, this is our x-axis. We've got 1, 2, 3, 4, 8. So our data points, there's 1, there's 2, 4, 5, and 8. And what's our average of this?
Oh, one should be five-ish.
What's that?
Closer to five.
Divided by 2.
Yeah,
Divided by 4. Wait, what is it exactly? 2.
4 plus 3.
Yeah, 4.75. So our average point lies like right around there. So that's our x bar. So then our deviance, what we would do is this is 2 minus our average, 4.75, and then we would square it. And then this one is 4 minus 4.75, and square it. And then this one is 5 minus 4.75, square it. And then this one is like that, 8 minus 4.75, and then we'll square. So in this case, these were negative, right? And these were positive. If we ignored the squares, if we didn't take the squares, the negatives, the magnitude of the negatives would match the magnitude of the positives. So when we take the square terms, it takes the negatives and makes them into positives. It starts to increase it. So our sum of squares is going to keep increasing and increasing and increasing. When we take the sum of those, so the sum of our x minus x bars and squared, so that's adding up all of those values. And then what we can do is do our sample minus 1. So if we just did divided by n, we're going to be, pretty low. We're going to be pretty biased, but when we take that n minus 1, it gets us to an unbiased estimator. I think that was a consequence of the idea that we're actually, instead of using mu here, which is our population, we're using our sample statistic to make that approximation. We're going to see the same thing for our analysis of variance, because what we're going to do is compare these sum of square values of each of our group to a group mean, and then we're going to look at the variation that's within each of our individual groups to see how much of our total variation is due to the differences between the groups and how much of it is just due to random variation itself. So we're going to use these sums of squares. We're going to use the mean squares again to kind of help better understand what ANOVA is actually doing. All right, so hopefully that cleared things up.
Yeah, I get it.
All right, so what we're gonna do is, I've got these dispersion practice, so you can see normally in a regular class we would be doing these things by hand as practice. So we're gonna skip the calculate by hand and just say, get those in R, check your answers in R. And what we'll do is we will pick this up at 2. So you're gonna have time either right now to do it, or as soon as you get in here, sit down, just get these, make a vector, demonstrate that you can calculate your variance and standard deviation. That's for these, and then your range and IQR of these. And then what we'll do in lab is I'll show you how we do it with a frequency table, how we calculate it by hand with a frequency table. All right? I think we are going to stop there. So my wife's roommate wrote back.
Oh yeah, already?
Oh yeah. Yeah, that's. So she said you have to spend 4 hours watching films, but to write about the films well, you need to watch them or at least scenes from them more than once. So the students need a week minimum to do well if they have the framework for visual analysis in place, which they probably don't. Oh man, what an absolute mess. Absolute mess. All right, so see it too.